Okay, 10 after, so let's get started. Couple administrative things. So I'll have feedback for the proposals back to you guys by the end of the week. So you should get some feedback pretty soon. And then next week, unfortunately, I have to be out of town for a conference for my other job. And so I will be pre recording the lectures again. Um, and I will make an announcement on Canvas of when I'm doing that in case you want to join live, which you definitely don't have to. Probably I'll record at least one tomorrow. But again, I'll let everyone know when I do that. Okay. Any questions? Okay. We're gonna pick up really quickly where we left off last time. And let's take a look at this plot here, which as a reminder is the plot of our predictions. So if you remember, we're looking at how the movie runtime and the rating of the movie correlate to the certificate. In other words, the movie rating, so G versus PG, PG-13 and R. And so this plot, you can see, looks pretty different from our multinomial logit and our LDA models, linear discriminant analysis models, which both need to have essentially straight boundaries, and that's an artifact of the sort of form of the model. But here, with a KNN, it's totally non-parametric, and it is just looking at the sort of closest points. So in this particular case, it's looking at the three closest points, the three nearest neighbors, and then filling in a prediction based off of whichever ones, like the three that are the predominant neighbors. And so, if I pick like a point here, it's saying it's red, and that's because the three closest points are red. Okay, and so, any questions about this? So, as I mentioned last time, the plot of this can actually look very different depending on the number of neighbors that you select, right, to actually do your prediction on. And so we can actually look at that here. And we can plot it. We'll wait a second for it to plot. It might take a while. There's interpolating quite a lot of points, and so even with my brand new computer, it's slow. I can probably decrease the number of points being interpolated to make it a little bit faster. One of the things is I did have a setting for alpha which kind of makes the shading of the predicted points a little bit lighter, but I did notice in the last one they were still pretty dark, which means that they're overlapping quite a lot. So if this takes too much longer, let's see. That is true. No, it's still going. It's rendering. Okay, and so as we wait for this thing to go, recall that the choice, okay, there it is, and then make it, okay, I guess this one also has to render, so however long that took, we'll wait a second. So just recall that the k's at our extreme ends, what are those going to look like? So the larger the number of points, the more uniform your plot should look. This looks a little bit strange, to be honest. There might be something funky going on here, but generically speaking, right, we remember that if I have a number of k, if my k is selected as the total number of points, then what color would it pick? Yeah, the most common, right? And so if blue happened to have the most number, then as this approaches the total number of points in your data set, then this whole thing will become blue, right? Okay, so then, yeah, okay, this is definitely, I think, no, this actually looks right. Okay, so here, if you only have one neighbor, so what is that going to look like? You guys noticing anything here? How well do I predict with one neighbor? What is my error rate?
Is it just what is the color dots fall in the color of the background? The fill? Like visually?
Yes.
I mean, it looks pretty good. The reds on the left side look pretty decent. Blues in the middle. I mean,
Well, okay. I mean, if I'm only selecting by one neighbor, then
should be the most.
my prediction should be how accurate?
Best. Pretty good. School roof fitted.
Okay.
Oh.
So it'll be, I should have an error rate of 0, right? Because you're basically saying, for this red point, if I'm on that, I only look at the nearest point, which is itself, right? And so when you're at k equals 1, you're on the other end of the spectrum from, only one color, right? So here, every single point will be predicted to be exactly on itself, and so overfitting, right? And so this is a little bit counterintuitive compared to the way we're thinking about it, right? So the smaller your k, the more complex the model, right? And so the more likely you are to be overfitting. And the larger your k, the more you're probably underfitting.
You said when k equals 1, it's only checking itself.
It only checks the nearest point,
Right.
as opposed to the nearest 2 points or the nearest 3 points. So then when I predict, when I do a prediction, if I took this point away, right, we can see this whole place is red, and so if I point to this spot, it'll be red. So this will have an error rate of 0, but probably will have an overfit prediction if we were to add more data points, or if we were to leave points out. Okay. So our ability to select any particular point heavily dependent on the k, and so we choose the k via cross-validation.
Yes.
That's the only thing you guys have to do. Yeah.
That's the fun.
It doesn't by definition have an error rate of 0 though, right? Because it's a nearest neighbor, not
Yeah.
itself.
That's
Yeah. No, I think it would, because unless you had 2 points on top of each other. So the thing is, like.
Oh yeah, okay. Because if you chose the neighbor as the point for.
Yeah, okay, so
location,
I'm the
yeah.
red point, okay, and then if I'm checking here, I look at my nearest point and it's
the same
red,
as the other guy.
and then I'm here and it's red. But if I'm like on top of the red point, it's still red. And so when I do the prediction,
Yeah.
it's you're predicting where I'm actually on top of it, and it'll be the same one. Yeah. So you could zoom into this and check individually, and you should be getting exactly the same. But if you left any data out, you would probably have a horrendous error. Well, possibly you would have a bad error rate. Okay? So yeah, this is totally non-parametric way of doing a classification approach. Great. Any other questions? Okay. So that's just kind of wrapping up last lecture. And so now we are going to jump to something totally different. Okay. If it will let me screen mirror. One moment. Hang on. Am I on the same Wi-Fi? Yes. Okay. Here we go. Okay, so today we are going to do a bit of a right turn, and we're going to talk about causal relationships. So almost everything that we've talked about so far has been sort of focused on this idea of prediction, where we really care about, and a lot of the like errors that we're talking about are kind of focused on getting your outcomes to match as close as possible to reality. So we do this, right, by calibrating our models, and then we also think about getting close to like an out-of-sample test set, for example. And so the better you can do at that, the better your model is at predicting things, and even predicting things that it's not trained on. There is, if I were to kind of divide data analysis in general into like two fields or approaches, causality would kind of be the other side of the coin. And so causality really cares more about the effect of X on Y, and identifying and going through specific procedures in order to do something called identification, which is to say, if I were to change something in X, I want to know how Y would respond, okay? And so this can be totally, I mean, they sound very similar, right? Because we're thinking about this model generating some outcome, but the big difference is in causality. You care specifically about those relationships as opposed to being good at prediction. And that's going to kind of drive you in a different direction when it comes to modeling. And hopefully we'll see that today. So I'm sure you guys have seen this before. Correlation does not always equal causation. This is one of the most common misconceptions, right? And one of the examples I can point to that we've looked at, right? So in the wages example, in fact, we saw something like how gender relates to wages, right? You saw that if you are female, females tend to have average lower wages than males. But is it a direct relationship between the fact that you are female that's leading to that, or are there like underlying factors related to gender that is causing that discrepancy, right? And so if it was a causal relationship, then if for example I were to switch genders, then you would argue that that would cause you to lose out on wages, right? But we know that that's probably is not what's happening, right? And so in order to determine a causal effect, you have to dig a little bit deeper. And we're going to figure out how to do that today. So the difference here, correlation talks about the relationship between two variables, whereas causation, one event is the result of the occurrence of another event. So the way that we're going to try and investigate this a little bit today is using something called a directed acyclic graph, also known as a DAG. So this is a finite directed graph with no directed cycles. And that just means it can't loop. So that looks something like this. X So we're not going to get too much into the theory of this, but you can think of the arrows as representing causal links between variables. And the idea, the sort of theoretical idea behind these graphs is that causal inference always flows in one direction, but statistical information can flow in either direction. Now, it's not too important to totally grasp at that, but some of the fundamentals of the statistical building blocks of what's going on behind the scenes depends on that relationship. Okay, so let's take a look at a specific example. So just as a reminder, so these as directly causes. Okay. Frequency of brushing teeth. This leads to gum disease. This can lead to inflammatory immune response. And ultimately leading to heart disease. Okay, so this is an example of a directed acyclic graph. Just some terms here. This would be a parent node. This would be a child node. And you would have something like this. Ancestors going up and descendants going down. Okay. And so if we were looking at just this plot, and this is the whole world right here, what are we saying about the effect of frequency of brushing teeth on heart disease? Is there a sort of causal effect? Yes, right? It's all linked in one sort of chain here. And so, in a regression setting, I might say heart disease is equal to beta frequency of brushing teeth. Okay? And if this were a causal effect, then as I change the frequency of brushing my teeth, I would directly affect the amount of heart disease on average, and that effect would be determined by this beta. Okay, so now let's zoom back out to the real world, and let's say I get a giant data set, let's say of a random segment of the population, and I am able to observe the prevalence of heart disease, and I also am able to observe the frequency with which they brush their teeth. What do you guys think about this beta and its representation of a causal linkage between frequency of brushing your teeth and heart disease? What do you guys think?
There could be some intermediary factors that are not, or I guess other factors, not just things that are related to how frequently you brush your teeth, but also are related to how often you
Yeah.
brush your teeth.
Yes. So the only thing I'll be extra clear on is that it's not necessarily intermediate, right? Because technically we're sort of capturing
Yeah.
anything that happens, but yes. I think your point is that we could have something like exercise, which might relate to heart disease, or diet, that could relate to heart disease. Right, and so this might be an overall thing of health, let's say consciousness. Okay, and so that's exactly right. And so what we say is that there might be some kind of confounding factor that is related to frequency of you brushing your teeth that affects heart disease, but may also be related to other factors that are related to things like exercise and diet that could affect heart disease. And so if I were to use this simple model, there may be something correlated between frequency of brushing your teeth and exercise and diet, right, as it relates to overall health consciousness, that would lead you to believe that might mischaracterize the relationship here with heart disease. And so, again, the sort of perspective is, with all of this information, maybe you could get, or let's say frequency of brushing your teeth is a very accurate predictor, or not predictor, like let's say this is sort of very well correlated to health consciousness. And so by controlling for frequency of brushing your teeth, you are also somewhat controlling for exercise and diet. And so from a predictive sense, I may do really good at figuring out predictions of heart disease. But from a inference perspective, if I were just to change the frequency of brushing your teeth, you may be affecting heart disease in sort of in a non-causal manner. And so if you were to go out and just get people to start brushing their teeth more, people who have poor health consciousness, just because they change this, it may not change heart disease, okay? So that's the really big distinction, right, between predictive ability versus this like causal inference that we're doing. Yes?
Is that an equivalent thing we need a direct path from frequency of brushing teeth to heart disease instead of have multiple paths for the two variables in between? Because in the DCA, it's require a direct connection between Y, which is heart disease, then X, and the equation would be frequency. If not, if no direct path, then we need basically write a lot of recurrence from frequency to heart.
Okay.
Isn't that right?
Yeah, so I think this is where I'm going, but
Okay.
let me continue down this path. So what would you try and do here? Our objective now is to really figure out the causal linkage between this and this. So what do I need to do? Or what do you think we need to do?
Well, only use those two variables, then we probably need a heart disease equal beta 1 of inflammatory, and then another equation, inflammatory equal beta 2 of that one, and then
So you're saying that
a series of equations that account for
The waterfall.
every path in between.
If you have inflammatory response.
Okay.
inflammatory
Wait, hang on. What would my other equation be?
The heart, okay, so let's only use the frequency to heart disease path. Then we have a beta 1, let's say beta 1 is frequency to heart disease, right?
Yeah.
Then beta 2, let's say from inflammatory immune system, then beta 3 is from inflammatory immune system to heart disease, then we have beta 1, 2, 3, and then that's the first equation is heart disease equal beta 1
Okay.
frequency. Then the second is inflammatory equal beta 2 heart disease. Then third one, heart disease equal beta 3 inflammatory immune system. And they now plus together, they're separate equations.
Okay.
Because the very first equation you write down there actually tells me it needs a direct path from frequency to heart disease, not accounting for everything in between.
Okay. Yeah.
Could you
I'm not
write
sure.
it similarly, but like, because if you're trying to compute it frequency of brushing teeth, then wouldn't you do, it'd all be frequency of brushing teeth would be the beta of gum disease, so it'd be frequency of brushing teeth, but that beta, so that the impact of frequency of brushing teeth on gum disease, then the frequency of brushing teeth, inflammatory response, and then all the way down the chain, so you have multiple betas, but they're all, it's like the waterfall of, so you're only using frequency of brushing teeth, you have, I guess, diminishing betas because you're like further away from like your outcome, like what you said, because you have multiple things.
Well, okay, hang on. So let me go back to this really quick. So,
I think that's because the very fundamental assumption of DC is every direct, like the error there represents an individual separate causal evidence. So I don't know if they can be classed together, like we do for linear regression.
So let's walk through this slowly. So the when I look at this sort of model, sort of individually, the issue is that here we're basically saying heart disease is being attributed to these things, right?
Only the first one. There's no second and third part.
Okay,
Only
good.
the first part.
So these two these are all correlated with each other. So you probably don't need to have these unless you think that there's some other arrows going into here.
So the heart disease is beta multiply inflammatory, no other two variables.
Okay. So
So
like
the
here.
one direct,
But if that were the case, then I have no, I still don't know anything about this. So just think of the world like this, okay? In this particular case, all of these things are related to each other, okay? And so, let's say you have frequency of brushing teeth. For every 10% this goes up, let's say this goes down by 5%, and every 5% that gum disease goes down, let's say this goes down 5%, and for every 5% this goes down, heart disease goes down 1%. So again, okay, so let's again forget about all this stuff here. Given this sort of direct relationship, what is the relationship between inflammatory immune response and heart disease? The causal effect that's getting described here. So 5% goes down, 1% goes down. Okay, what's the causal linkage between this and this? Yeah, 1 to 1. So 1% goes down, 1% goes down, or 5 to 5. What's the relationship between gum disease and heart disease? 5% goes down, 1% goes down. Okay, and then what's the relationship between frequency and this? 10% up, 5% down. And then what's the relationship between here and here?
10% up, 1.5 down.
Yeah, so 10% up, 1% down. So having this diagram lets you understand causal relationships between each of these things, but if I were specifically concerned with this, I actually don't need to know the stuff in between. I don't need to control for the things in between here, unless I suspect that there are other things affecting these variables, right? So,
If you include all of them together, do you run into some sort of a multi-collinearity problem?
okay, so,
Nesting them or something?
Yes, you have
Here we
all
go.
these coefficients and the whole chain.
yeah, okay, so we're getting,
A nesting one.
Yeah.
we're getting to maybe the right track here. So we understand this portion of the plot. So let's say you have heart disease is equal to beta 1 frequency of brushing teeth plus beta 2 exercise plus beta 3 diet. So then, in this case, you are essentially controlling for all other factors that go into heart disease, right? And so by doing that, you are effectively sort of isolating, the effect of frequency of brushing teeth on heart disease. And so in this model, as we've generically sort of created this model, this would be a way, essentially, of breaking the statistical path of these guys as it relates to frequency of brushing teeth through health consciousness, right? These guys are essentially controlling for health consciousness in aggregate. Okay? Now, going back to sort of reality, if we had a big data set on heart disease, frequency of brushing teeth, exercise, and diet, and we ran this model, what do you guys think about the causal effect as described by beta 1 of frequency of brushing teeth on heart disease? Are we good to go?
I mean, doesn't it depend if you want to disentangle the health consciousness effect
Yeah.
into exercise and diet, or do you want it as one overarching explanatory factor?
Well, okay. So don't get too complicated. This is what we care about, understanding the causal linkage here. Do we believe that this model in the real world would be an adequate way of figuring out heart disease, the causal relationship?
Parts of it. Exercise and diet. But assuming that we believe that brushing teeth can have an effect,
So we're no longer confined to this. This is our hypothesis model.
Mm.
Okay. So what might be going on Yeah.
We might be missing the descendants that's gum disease and inflammatory immune response that then lead to heart disease.
Well, no, I mean, we've described that this pathway
Mhm.
is straightforward, right? It's not descendants of this thing, right? Because that's all controlled for up here.
Within the brushing teeth.
Yeah.
corridor.
Yes.
You're saying in the real world with other variables not missing. Predisposition, so genetics, what's your family history, like
Okay.
other medical like factors.
So there could be other things, right? There could be other things related to heart disease. And so ultimately, the kind of strategy to take here is effectively trying to get rid of this line here. And so if you are able to do that, then we can infer that whatever we derive for this value will be like a real causal relationship. But the issue is that there's information flowing here, sort of causal inference direction, and statistical information, which we can kind of try and leverage to break that linkage. And so conceptually, the sort of strategies that we use to determine causal inference is essentially doing things like this. Okay? And so we'll take a look at some of these strategies. So the general problem looks something like this. You have X going to Y, and if that's the thing that you care about, unfortunately, you oftentimes have some version of this going on. So our unknown error is confounding the effect of X on Y. So we don't know if changes in Y are a result of X changing, or if they're a result of something that we don't see in the world or not captured in our data. Something else is changing. So there are 3 common methods to determine causality from X to Y. So one is the back door. So this block all indirect paths from X to Y, but leave all direct paths open. 2, you guessed it, it's the front door. So all direct paths from X to Y pass through a mediator variable. So that might look something like this. And lastly, and probably the one most commonly used and one that you guys may have heard, is to use an instrument. So use an instrumental variable which affects X and Y only through X. So that would look something like this. X going to Y with a U, and you have your instrument doing that. Okay. The front door and the back door are both a little bit less common. It's harder to get a mediator variable for all direct paths to Y. So if you imagine our, let's see, here, that would mean that I would have to have some mediator variable here that all of these paths go to before I get to heart disease. Okay. And so generally speaking, coming up with a variable like that is going to be pretty tricky. It's a pretty rare context to find something that could fit there. Whereas an instrumental variable might be something here that goes here. So what would example of an instrumental variable in the context of this particular problem be? That would mean you would have to find a variable that only affects heart disease through the frequency of brushing your teeth and not through any of this other stuff. Maybe.
Dental insurance.
Yeah, dental insurance. So,
So I
Genetic
tell you to brush your teeth.
predisposition.
wait, hang on, I'm trying to follow. So this is like the art of like econometrics doing inference, like people propose these instrumental variables and then you have to like think about the logic of it and then defend whether it makes sense or not. So let's do this one really quick. So dental insurance, so the idea is that if you have high dental insurance, you would want to like brush your teeth more or less or something.
Well, it's yes or no, dental insurance.
Oh, do you have dental insurance? Okay. So, would people with dental insurance brush their teeth more or less, and why?
I would assume more because they were reminded by the dentist.
Okay, yeah. So then, yeah, so then I might even, yeah, I was actually gonna say like some kind of dental reminder, but maybe that's like a good proxy for that, because you wouldn't be able to measure that. But, okay, but.
And they can tell you if gum disease is starting and all that.
Yeah. Although, okay, wait, but then,
And it's not going through that.
yeah, then you're in trouble, because then
Branches.
dental recommendation, yeah, if it goes through here, then you don't know if the dental recommendation is like affecting your gum disease in some way. But let's say it's not, right? So then the argument, right? So like if you could count or if you could like quantify like a dentist's recommendation for you to brush your teeth, then that could plausibly be an instrumental variable, right? It would flow through here, it would affect how often you brush your teeth, but we could plausibly say that the dentist saying, brush your teeth, isn't gonna make you exercise more or, well, or change your diet. Let's say they're like, you can eat whatever you want, but brush your teeth more, right? So then plausibly, your instrumental variable wouldn't go through either of these, it would only go through here, and if we could measure that, then you could control for changes in this that wouldn't be affected by this and health consciousness overall. You're breaking that link. Okay, and so that's essentially the way that the instrumental variable is working.
So you just find data on that instrumental variable, make a variable out of it in your code.
Yeah, I'm gonna show you how to do that. It's actually kind of straightforward. Essentially what we do is we run 2 regressions. Our first regression is, this is our outcome variable, and the dentist thing is the income, is the explanatory variable. And then we take our predictive one from that and then plug it into this bigger model here. And then the new beta will be representing the causal effect, because you've controlled for how this is changing in response to the instrument without these things changing. So the procedure to do the instrumental variable, as we walk through it, hopefully it'll be pretty straightforward. The most challenging part is actually this part where, when someone does their presentation of an IV regression, they stand up here and half the presentation is spent defending the instrument, and they're saying, no, it doesn't change exercise, it doesn't change diet. It definitely only goes through here. That's most of the hard work is actually picking a good instrument. Okay? Yeah.
And is this only done through theory and logic, or do they try regressing that instrumental variable with exercise diet to show that there's no...
Yeah, well, there are a couple of different tests and stuff to show that it's a decent instrument and everything. But yeah, this is also one of the points we'll all go back to, kind of the difference between the predictive aspect and the inference aspect. Doing this procedure, this IB, if you do a 2-stage least squares, which is the procedure to do this, it actually makes your predictions usually worse. Almost always it by definition almost has to make it worse, right? Because you're introducing a lot more noise into your explanatory variable, because you've done this first stage of progressing on it first. And so any errors that are a result of that first stage of regression get propagated through in the next one. So your standard errors are almost always going to be bigger, and oftentimes your predictive ability goes down. But the trade-off that you're making is that you don't really care about that, or you really care about this beta and whether or not it's actually having this type of relationship that you're interested in measuring. Okay. So we are going to look at a data set, a different data set with this example here. So I'm going to look at BMI. So this is body mass index, a very sort of generic indicator for health. It's not really an indicator for health, but we'll go with that for now. And look at how this is affected via a number of demographic variables, whether or not a person is pregnant, and their level of education. And then we are interested in the causal effect of smoking on BMI. So if I were just to run a regression, beta 1 income plus beta 2 age plus beta 3 gender plus beta 4 pregnancy, and so on and so forth, equals BMI, would that help me determine the causal effect of smoking on BMI? No, and why not? What might be a potential issue?
Other factors might also be taken into
Okay, so say you have social opportunity or something. And this could be related to whether or not you smoke and your level of education, right? And so right here we already have a problem, right? You can't determine causality because of these sort of relationships, right? You don't know if it was intrinsically something that was upstream leading to this having an effect that's correlated, right? So what we're going to do here is to look at an instrumental variable in order to determine whether or not smoking has an effect. And we're going to look at a couple of different examples of instruments. And we'll jump back to this chart in a little bit. Okay. Get out of here. All right. So I already uploaded this to Canvas. There is a data set called PS6. This is a tab separated data set. And so we can see what that looks like here. It has all of the variables I was talking about. ST-FIPS is a location indicator. Here, income squared, age squared, whether or not they're female, whether or not they're pregnant, level of education, and then whether or not they smoke. Okay? And there's a couple other variables there that we'll go through in a little bit. Okay. I'm just going to get rid of any NAs. And let's look at the OLS example. So this is going to be linear regression of BMI income squared plus age squared plus female pregnant education and smoke. Okay, and we can look at the results of this. Okay. So here we're running our generic linear regression, and we can see how body mass index is affected by things like your gender, which makes sense, right? There's difference in BMI between males and females. Age makes a big difference, but then none of these other things are statistically significant. Well, actually, so I shouldn't say that, right? So education, these aren't different compared to the baseline level of education. They're statistically different, but that in itself does have some effect. And then we can see smoking, not statistically significant, and it would have a relatively small increase in BMI if they do smoke. Okay. So this we all kind of know how to do. And now we're going to look at the instrumental variable using a 2SLS, which stands for two-stage least squares. And we're going to use unemployment as the instrument. So two-stage least squares. Actually, I didn't go through this. So in a two-stage least squares regression, essentially all you're doing is we are first going to run the regression with the variable of interest that we want to determine the causal effect on. We want to see how the instrument affects that, right? Because everything has to go through, or the effect of the instrument on your ultimate outcome only goes through your variable of interest. So here is stage 1 model using the unemployment variable. So now our y variable is smoke plus all these other things that we want to control for. So in our previous example with the dentist, right, you're saying, I'm going to control for how much the dentist affects the frequency of brushing your teeth, and I'm also going to control for how much the diet and exercise affect someone brushing their teeth, right? So the sort of backwards flow of information. And so in this case, it's all these other things that are changing. We control for those to see specifically how unemployed, fix that, how unemployed affects your smoking variable. Yes?
Is smoking be a factor or not?
Smoking is a factor, but I think it'll do it automatically, yeah. So what we do then is we generate a new variable called smoke that has gone through the first stage model where we're just predicting on that model. And then we're going to rerun our original linear regression, except we're going to change this factor into whatever was predicted from here. So all the same stuff. Plus now, instead of factor smoke, we're going to do this. Oh. Okay, so forget about the standard errors for a second, because actually when you do it in this manual way, these standard errors are going to be computed incorrectly. There's actually a package I'll show you guys in a second that does all this and then computes the errors correctly, but essentially now what we're seeing here is that once I introduce this instrument, I have a much larger different effect, right? So before, so right now it's saying 17 for a change of 1 in smoking, or 17.8, whereas before it's 0.3, okay? And so by doing this sort of procedure and controlling for things, you can end up with much different effects. So now, let me go back to here. So just to summarize what we were doing, in an OLS, we have y equals beta x plus this. In a 2 SLS or IV regression, we are doing x is equal to a different regression, x hat is equal to this, and then ultimately we do beta x hat. So this is first stage and second stage. Okay. Hopefully everyone can see what's going on here. Instead of this, we have an x hat, which is the predicted value of our variable of interest coming from the first stage. Now let's jump back to here. And so what we looked at right now was unemployment. So this is the new model that we're sort of hypothesized. What do you guys think of this model? Yeah.
But unemployment could also affect income. So
Yeah, probably, right? Yeah, so you probably have stuff like this happening. You probably have something like this, right? Age probably affects your employment. Education probably affects your employment, right? So what would we say about this instrumental variable?
not a good instrument.
It's not a good instrument. This is a trash instrument. So we need to think of an alternative variable to here that only affects smoking and is able to get away from the relationships with all these other things and from even things that we don't even see. Okay, and so that's again the hard part and the sort of art of doing this sort of instrumental variable regression approach. So we'll get rid of all that stuff and let's take a look at the data. Let's try, there's one last variable here called cigarette tax. Okay, so let's take a look at that. We're going to do the same thing here. This first stage of the model, we're going to do a linear regression, same as before. Except this time, instead of unemployment, we're going to use cigarette tax. And we will do our prediction here. And actually, we can even take a look. So when I run this, I'm going to do a summary. So the cigarette tax variable is just saying if you live in a specific place, right, that whether or not there's a cigarette tax. And also, in different periods of time, is there a cigarette tax? So there's variation in both location and in time for that.
So that's a dummy variable, right? If there's a cigarette tax, it's 1. If there's no cigarette tax, it's 0.
No, it's an amount. How big the cigarette tax is.
Wouldn't that be related to your income somehow? So if you're more well off in terms of how much you earn, more likely you are to be impacted by the cigarette tax?
No, okay. No. You're doing it backwards. So how much does cigarette tax affect the amount that you smoke?
Higher cigarette tax would probably reduce the amount you
Right.
smoke.
Generically.
Yeah.
So it is not saying that people with different incomes would be subject to a higher or lower cigarette tax. That's the distinction.
Oh, so it
So
applies
income,
regardless.
yeah, so income can still affect the amount that you smoke, but we control for that, right? But income isn't affecting the cigarette tax itself. That might be different if it was like,
A
in-
progressive or regressive cigarette tax? in a
yes,
way?
yes. So when you go to buy cigarettes, they ask you for your income. You have to show them your W-2, and then they scale the tax based off of how much you make. So that's not how cigarette tax works. So in this case, right, let me jump back to our diagram. Do we plausibly think okay. Does the presence of a cigarette tax in this sort of relationship plausibly make sense? Right? In the last one, we were like, unemployment definitely is related to all these things, right? So does how much money you make affect whether or not there is a cigarette tax in a particular place? Does how old you are? Right? So all of these things. What do you guys think?
Income might be like a medium-term variable or something
Yeah.
that goes between cigarette tax
Because-
and smoke, because you might be less elastic to the tax if you earn more. Like you might be less willing to change based on the tax.
Progressive cigarette taxes. I told you.
Yeah, I was actually thinking of something else, which is that
So is it the fixed amount, like per pack or something, or is it the total cigarette tax payment you make as an individual?
no, it's like an amount per
Per pack.
pack or something.
Okay.
Yeah. I was actually thinking
Higher state taxes.
that if your income is related to where you live and the cigarette tax is only in certain places, then there might be something there. But actually, in this data set, they've kind of cleverly controlled for that because they have a before and after as well. So it's not just location based, it's also time based. So you could be in the same place and not experience the tax, and then later experience the tax, and see how smoking changes, right? So we're okay on maybe one of the concerns that I would have, but then you were saying that income could be mediating the effect of the tax on smoking.
Why
Yeah.
isn't it more arbitrary though? Because as a policymaker, if you're thinking to apply cigarette tax, do you pick places where people of certain income ranges live and then set it?
No.
It would.
No, it's just,
Yeah. So, but
it's probably not.
then how is income determining?
Well, this is kind of a stretch, right? I mean, this is the type of thing that you would kind of try and work through and defend if you're doing this as like an actual thing. I don't have a great response to your concern, but I would say
Purchasing
Or you
power.
could just look at like different income brackets, right?
yeah,
Like, look at the
exactly.
relationship across
Quantify.
different income brackets
Yeah.
to determine what that.
So
relationship
you
was.
might have something like a an interaction variable between income and cigarette tax. Like that's possible to include that. But actually,
Wouldn't you do
that
income
wouldn't-
and smoking and then look at the cigarette tax? Or
well, hang on. So if you did an interaction, I don't think actually that works because now you have now your instrument variable, like this is not the only path that it goes into your causality. So yeah. So if an economist were up here giving this presentation and then you question them like this, like that's the essence of a lot of the work that goes behind getting a good instrument and demonstrating that your model actually works. It can all fall apart if someone comes up with like a clever reason for why why it shouldn't work. Yeah. Okay. So what was your comment?
I was thinking like the interaction term, if you look at like, if you wanna look at like the impact of a cigarette tax on smoking, or eventually to be my bit, so looking at smoking first, right? So isn't it like, would it be like the propensity to smoke based on income, and then how the cigarette tax impacts that relationship?
I need a question
Is that a way to think about it? Would that be a good interaction for the user? Would we
to do
income and smoking, and then see as an interaction to see what the
no. So always so if you're not sure, always go back to the diagram, and if you had a variable, if I had a variable smoke times income here going like this, you would have something like this, right? Cigarette tax, the path to from cigarette tax to BMI is no longer only through smoke. So you're no good. Yes.
So it seems like in practice it's really hard to find the instrument
Yes,
variable
it is
that-
very hard.
A question is, statistically, is there a way actually we can follow to maybe just find out the skill if the relationship is small enough, we can lose that assumption because the data is
Yeah.
always bounded to
Yeah.
something.
So the relationship between this and this determines what's known as the strength of an instrument.
Yeah.
Okay. And so the worse the relationship between here, like even if this is all theoretically super sound, so let's get rid of all this stuff
If
here.
the theory are tested by data and you can't
Yeah.
it's not practical calc every aspect
Yeah.
of the
Well, yeah, but let's say that this is the perfect model, okay? Like in terms of, like my defense of the instrumental variable is like super solid. No one can come up with any reasons why this doesn't work, okay? The relationship between these two could still be really weak, in which case you have something known as a weak instrument, which introduces a whole lot of noise, and then you could have like really big standard errors on everything, and the effect, like even if it's a causal effect, it could be like totally insignificant.
What about we argue there's a relationship between income and securitize, but we actually really care about the strengths between smoke and securitize, and is a way we ties to the strengths among those two relationships. If the relationship between income and securitize is really weak, well then it's probably the securitize with smoke relatively strong, like we lose that assumption there's nothing going on between securitize and income.
No, yeah, I see what you're saying. So practically, so what you're saying is, what if there is a relationship, but it's really weak?
Does
So
that support the strong relationship between securitize and smoke?
no,
Also evidence-
unfortunately, even if you have something like this, people will be like, no, that's basically no good. Because the problem is, now that you've introduced this, you don't know the portion like this. There's this relationship happening here. You don't know the contributing effect of income on smoke, even though we denote that this relationship is weak. It could be that like it's still having some effect, right? So you can't make any conclusions about the causality of this on this because of this relationship, even if it's weak.
Oh, I think that relationship doesn't come from theory perspective. If people say, okay, why don't you test other things? And we use the data to test it. Actually, that doesn't build on theory.
Yeah. So okay.
Evidence to support why you choose a securitize in the first place.
Yeah. So
I think it's the other way around.
yeah, I know. Because what I'm about to say is right that like all of these things affect. Well, actually, we're not looking at the effect on cigarette tax. Yeah. So my understanding is that even if there is like a relatively weak relationship between your IV and other sort of variables, it's difficult to discern whether these are like random correlations or things that are like actually real, right? Because I could take bundles of different variables and things could be highly correlated just by chance, but that would have no relationship with each other, right? And because of that, we rely more on the like theoretical and qualitative logic of relationships than looking at those numbers, right? There's like you could take things that are like totally uncorrelated, and you could run into issues, or two things that we know have no relationship to each other but would have high correlation, and you would run into issues if we were just going by the data, unfortunately. Yeah.
That's true.
Yes.
No, I'm just
Okay. All right. Yeah. So in this case, I actually did a summary of our first stage so we can actually see how all these factors relate to smoking directly. Specifically with the cigarette tax, we can see the cigarette tax actually is a weak instrument, even if we think that it's like a good one, right, logically. The effect on smoking is very small and not significant, which is gonna like make a lot of the results that we see out of our model probably insignificant when we actually do it correctly with the correct standard errors. Okay, so let me finish this guy up.
I'm sorry, you said we know it's because of which value in that summary?
So the whole idea, right, is that you're getting this relationship between your instrument and your causal variable. And so that's what's being shown here is our first stage where we
Yeah.
run the regression on smoking. And so cigarette tax, the effect of cigarette tax on someone smoking is it does cause them to go down, but it's very insignificant
Based on,
on your standard error.
yeah, okay, yeah.
Yes.
You said these standard errors are not right standard errors?
The second stage won't be correct, but the first stage is. So forget about these guys here, and we can just look at the coefficients. In this case, actually smoking causes a huge increase in BMI. It's 137 if you do smoke. Okay, so that is essentially what it's saying here. Yeah.
But since we know that the cigarette tax is appropriate for smoking, so basically this is a garbage result.
No, we'll see what happens in a second. What will happen as a result of that is that the standard errors get blown up a
Okay.
lot. Yeah. So obviously you don't have to do this manually, like making you do a lot in this class. There is a library. Oh, okay, hang on. Did not install. Install. Right, because this is a new computer. I swear to God, I've done this like 5 times by now. Yes. Great.
Doesn't it automatically install the dependencies? Or do you have to-
I don't know. I had that in my code, so just in case. Wow, this has a lot of stuff, huh?
What is AER?
It's a economist thing, American Economic Review or something. AER is like the most famous econ journal.
Oh, yeah, okay. Econ journal. Oh.
Yeah. Here, let me see. AER.
Package stands for Applied Economics with, not economics, econometrics with R.
Oh, okay. I always thought it was named after the American Economic Review, but okay. That makes more sense.
Is that really exponential thing?
Oh, I had an error. Huh. Hopefully this works. Okay, that's fine. Okay, so this uses a function called IVReg. So we have our standard formula. So this is BMI, income squared, age squared, female, pregnant, education. Okay. Once you get to your variable of interest, that we want to look at the causality, you have this notation here where we have a vertical line, and then you write out the rest of the variables that you're using in the first stage. So something like this.
This is what we just did by hand always.
Yes. So this will do everything at once for you instead of doing it each stage separately, and this will calculate the correct standard errors. So we should be able to see what this looks like. So these coefficient values should be exactly the same as before. So we know 1.372 e to the 2, and if we look up, okay, let me just rerun it so we don't have to. Yeah, so 1.372 EO2. So all of these will be the same, but note that the standard errors are way bigger. Okay, so this is several orders of magnitude larger, and where this was statistically significant at the 10% level before is no longer significant, and that is a result of the fact that that's an artifact of the fact that your cigarette tax and smoking or causal variable of interest have a fairly weak relationship. And this makes sense, right? Because you're basically saying, based on the information about the cigarette tax, I am predicting smoking outcomes, but I'm very, very uncertain about that, right? And we know that from the first stage. And because I'm uncertain about that, there's like a large degree of uncertainty as it computes into the second stage, and that translates into your standard errors here. Okay. So that is the sort of general procedure to do IV instrumental variable regression, and that is a specific application, right, of doing causal inference in order to determine this whole causality thing. And again, this is like a very different worldview of running these sorts of models compared to the sort of predictive side of things. And this type of work is much more common for economists. And so when we think of like the field of econometrics and the sort of methods and approaches that economists take, it's much more going to be in line usually with thinking about inference. Whereas if you are moving more towards like stats and machine learning, that world is much more engaged in prediction, right? And so it's not necessarily one is like better than the other. They're trying to achieve like very different things. Okay.
Yeah, I agree. So the IV reg, so it's the stage 1 model,
Yes.
those components,
Mm-hmm.
and then,
Stage 1 is smoke and this.
sorry, sorry.
And stage 2 is everything.
So why, the order at which we do them is important, but why do we do, because we want BMI to be the outcome, but we want to do it over BMI, regress on BMI.
Yes.
So we have to do,
It's just this is your second stage here,
okay,
and then when you get to your causal variable, you have this thing to indicate
in the next stage.
that it's the other stage, that it's the first stage.
So it's always,
So just to reiterate, yeah, the bigger challenge of this part is not running that function. It's like figuring out the right instrument. And as we've seen here, even in our example, maybe there's not something that's maybe still a little bit fishy. I can tell you guys about an example of, I think, an instrument. So this is from a paper that I wrote many, many years ago. And kind of to show you, or give some perspective about like an instrument that I think works. It's been published, so it's probably right. But the idea was we were looking at how does the amount that you drive change as a function of gas price, right? So we want the sort of elasticity related to this term as gas prices changed. But as you can imagine, there's like tons and tons of things that affect your VMT. And so we need to come up with a really novel instrument for gas price, right? So we have gas price going to VMT, and then you have a bunch of stuff here. So we were actually specifically looking at gas prices in Pennsylvania and VMT in Pennsylvania. So the instrument that we came up with was oil rig shutdowns from hurricane activity. So, in the Gulf. Okay. So there's these hurricanes, right? During hurricane season that roll through the Gulf of Mexico, where you have a lot of oil operations. And so when the oil rigs and even local refineries shut down, that can affect gas prices all around the country. Right, it is a supply shock. But arguably, like the hurricane activity isn't, if it's located specifically in the Gulf of Mexico, it's probably not affecting like local aggregate VMT in Pennsylvania, right? And so this is an example of how this instrument can only affect VMT indirectly through gas prices and not through all these other things. Are you about to find a flaw in my...
No, I'm sad.
Novel paper.
What were the other things? Dots.
Oh, I don't know, just like tons like demographics, unemployment, GDP, stuff about the vehicles. This was like a decade ago. Yeah.
You specifically selected shutdowns in the Gulf because there was some percentage or some quantity of gasoline that went to Pennsylvania that was...
It doesn't even need to go directly to Pennsylvania, right? It's a supply shock in the system, so like other places might be. It may be that you get a lower supply into Pennsylvania from local refineries that are then sending fuel to other places to make up for that supply, right? Generally, it just means that you have a lower amount of supply.
Did you pick I'm just curious, did you pick like the refineries that were producing the type of crude that went into cars? This was like
Yes.
heavy and light.
Yeah.
If you had GDP in there, wouldn't oil rig shutdowns from hurricane activity in Gulf have an effect on that? So if there's oil rig shutdowns, you have, let's say, their entire export sector not producing, loss of jobs and employment, less money on their hands to buy imported goods from the US, and that then affects the GDP.
No, but these are
Domestic.
very like small scale things, whereas GDP is measured, and it's like localized GDP, right? In Pennsylvania, that's measuring basically economic activity in Pennsylvania.
Okay,
It was peer reviewed, so
yeah. I'm like questioning.
come here to get under fire for my old research. But yeah, generally, right, this is kind of like a really obscure variable, right? Yeah.
So that's like a list of dates or whatever, there's a shutdown,
Mhm.
and then there's like a calibration period, that's when there's not a shutdown.
Yeah.
And did you consider like the months of the year, like summer months when people are driving on vacation?
Yeah. So
all
you
of that, try to
control.
control for that as well.
You want to control like this U part. You want to control for like as much stuff as possible. That helps you get out of trouble with like other issues.
Consider.
Yeah, exactly. So yes.
So when you did this, what was the process you used to arrive at that instrument variable? Is it simple as like we
Oh,
went on a
you-
big whiteboard and we started mapping things out of like what
Yeah.
the different components could be,
Yeah.
and then we kind of settle on something.
You bang your head on the wall for a while until you. I don't remember honestly.
That's the process.
But it very much is like this thing, right? Like, if you're sitting here as an audience listening to someone talk about instrumental variables, like all the economists are like chomping at the bits to try and foil you. And that happens at like go to any econ talk that has instrumental variables, and that's like always there will always be at least 15 minutes of questions of people being like, oh, but did you think of this thing and like this weird relationship that goes like, yeah. So be prepared if you're doing this type of work to, like, most of your defense will be spent here. Okay. Great. I think we'll end like 5 minutes early today. And just
the result?
huh?
What happened?
Oh, what happened? It was like basically what you would expect, like gas prices. As gas prices go up, VMT goes down, and the elasticity is relatively close, like in the range of like what's seen in the literature, right? Because like this type of relationship, people have been measuring for a long time. So we were in the ballpark of where everyone else has measured. Yeah. For those who weren't here right at the beginning, did want to note, so next week I will be out of town. So I will be pre-recording next week's lectures, and I will make an announcement on Canvas when I'm doing that if you want to join live, but you're not required to. And I'll probably be doing one tomorrow. Okay.